Hello and welcome to our training sessions. This first session is on creating 3D cultural heritage models from photographs. It's a process called photogrammetry. My name is Dr. Andy Holland. I'm a research fellow in architectural heritage in the School of Civil Engineering at the University of Leeds in the UK. So, what is photogrammetry? Photogrammetry is a method of extracting measurement data, or metry, from photographs. It's been around for quite a long time, since at least the 19th century, although it really became established during the First World War as a way of rapidly producing maps of the conflict from aerial photography. Those early maps were and methods were very slow because you had to hand measure the photographs and apply a lot of mathematics in order to get information out of them. The photographs also had to be taken in a very precise manner in order for them to be of any use. Those manual methods were later mechanized through various very complex machines, like the one at the bottom here, to try and improve the that method and to make them a little bit quicker, but they were still kind of slow and complex. They still required the photographs to be taken in a very particular manner. Modern computing, however, and digital cameras especially, have revolutionized the use of photogrammetric methods. We can now use them for 3D modeling as well as creating maps. So where's photogrammetry used? Its strength really is the fact that the collection of the data can be very simple. You only need a camera, and that camera therefore is a quite quick way of collecting data. Therefore, it's really good for things like forensic examination of scenes, whether that's a crime scene or a car accident or a collision. And those are really good because you want to be able to record the scene very quickly, and then be able to reopen the road or the building, and it also means that you're not losing as much information or evidence because it's windy or whatever, or it's raining, etc. So you get the scene very quickly, and you build up a detailed picture, and you can see that from the bottom corner here of this collision between two lorries. In architecture and engineering, it's used for measuring buildings, existing buildings. You can use it to as the base model for visualizing things like airflow modeling, wind modeling, noise impact modeling, thermal modeling in terms of thermal absorption of buildings or reflectivity of buildings. And you can use the photogrammetry to create those base models that you build those on. It's also used for surveying existing structures, and very useful for architects, for instance, if they're extending a building or adding another building on next to one, and they want the two to be similar or to be in sympathy with each other, or just to see what the sight lines, for instance, are from windows, etc. You can use it to reverse engineer equipment by creating a model of a piece of equipment, and then testing to see whether that piece of equipment's been or part has been manufactured to the right tolerances and sizes and shape. You can also use it for stress and deformation analysis using the same principle. And finally, it's been used, its traditional method that I've already talked about is for surveying and building of maps and cartography, but it's also now used in building information management, or BIM. So in cultural heritage, it's very similar to the architecture in some ways. We use it for recording 3D archaeological sites, both during excavation and also monuments that are existing in the landscape. And it's very useful for that. Again, it's a very quick way of covering a relatively large area, especially using drones. We also use it for modeling 3D objects. So you can take an artifact that's been excavated, or it's in a museum, and 3D photograph it and create a 3D model of it. That can allow us to do further analysis that might not be possible on the object because it's fragile, or it can also allow us to present it to the public and allow people to handle a copy of it that's made through 3D printing, for instance. We also can use photogrammetry in these 3D models to look at the conservation and the preservation of objects and buildings by building 3D models sequentially through time. So building more than one model of the same object or building at multiple points over time, and looking at the difference between those models as the building degrades or the object degrades. And by comparing them, you can actually do mathematical comparisons and measure the amount of abrasion or damage to a building or an object, swelling because of moisture absorption, etc. Finally, access to restricted or destroyed sites, especially in areas where you've got conflict, where access to the site may be dangerous for individuals. For instance, at Palmyra in Syria, it's been done extensively. And also there where you've got sites that have been destroyed by ISIL, then you can use old photographs to reconstruct those buildings virtually, so that people can still look at them and still understand them, even though that they've now been blown up and damaged. And finally, in the entertainment industry, it's used a lot by film, computer games production, and CGI specialists. It's good for that because it's quick. It gives them lots of information on color and shape at the same time. And so if you've played computer games, a lot of the faces of 3D characters in those games are probably based upon photogrammetry in order to get realistic expressions and facial shapes. And obviously you can use multiple cameras to take a photograph from all of them at the same instant, which gets around some of the movement problems in cloth and hair that we see, and we'll talk about later. So how does it work? Cameras record the 3D world onto a two-dimensional medium, whether that's film or a digital sensor. And light rays entering the camera through the lens cross over at something we call the perspective center, or the focal center, and are projected onto the rear plane, whether that's the film or the digital sensor. Now, because you've condensed the world into 2D, we lose the depth information between the camera and the subject. And therefore, if you imagine this point here, noted by a capital A, this point could be anywhere along this red line up to the focal perspective center, and it will still produce the same point, the small letter A, on the film. However, it has a mathematical relationship from this point to the center of the film. It's the same as the center of the view to the point in 3D space. And because that relationship is fixed and it's a mathematical relationship, we can use that from multiple cameras to reconstruct the depth. So the underlying principle is that the same object viewed from two slightly different positions results in different images. So this small ornament from my house that I photographed from two positions appears slightly different. And comparing those two images, and especially comparing the mathematical relationships between points on those images and the center of those images, we can create a mathematical equation to work out the depth of the of that point from the camera, or from each camera. And that allows us to reconstruct the 3D position. By combining multiple points in each of these images, then we can create the 3D structure of the object. And that's why we call it structure from motion, because the camera moves and therefore there is motion. And it is that motion that gives us structure. And this is exactly the same principle that your eyes work upon. Your left and right eye are in two different positions and get two very slightly different images of the world, and therefore can reconstruct depth. So basically your brain is an incredibly fast photogrammetry processing machine. It does it instantly. The computer version takes several hours. So if I flick back and forth between these two images, you can see left and right eye or left and right camera see slightly different pictures. And the further away the object is, then you see different amounts of variation in the image. But unlike the human eye and the human brain, human vision, the camera can't detect and understand points in an image. It can't understand the world around it. It's just capturing data. And that's why you need the computer. So to be able to put the same on two separate images, then you need the computer to be able to recognize points in an image. We call this feature extraction. So in this image of a sheep bone from my PhD, where I was studying animal bone, then this tiny stain on the surface, when you zoom in, creates a pattern of color, which is just mathematical information really to the computer, in the grid pattern of the pixels on the camera sensor. Now color is expressed as 3 numbers from 0 to 255 of red, green and blue. So that's mathematical information the computer can use. We've also got the X and the Y coordinate of each of these points on the camera sensor. Now again, that's mathematical information. And they can combine all of that to recognize features. Once the camera's recognized the features in all the images, it needs to match images that are of the same subject and of a similar viewpoint. Once it does that, it matches the features it's extracted in each of those and matches them together. So it's identifying where features occur in more than one image, which is what we need for reconstruction. And then it does the structure from motion analysis and creates the 3D shape. That creates a cloud of points in 3D space. There's a lot of noise created when you do that. So there's a filtering stage that gets rid of some of the bad data. The computer then does depth mapping to map in between those points and create more information. You then mesh those 3D points so that they're no longer a cloud of points, but you turn them into a surface made up of triangles. And you then add the color information, and we call that texturing. Fortunately, because we're using photographs as our source material, then we can take the color information from the photograph and combine it to create a texture for our 3D object or 3D building. However, there are some subject materials that don't work very well. So for instance, anything that's untextured, it has no surface information and nothing for the computer to be able to recognize as a feature. So like for instance in this completely plain white bottle, then the computer has great difficulty reconstructing the 3D shape because it can't match any points. Equally, highly reflective or transparent objects have the same problem. So this clear Play-M jar, the light rays that are coming into the camera, and therefore the computer is interpreting, aren't coming from the surface of the jar, but are rather coming from the rear surfaces and reflected off the environment around it. And so they don't reconstruct. So basically anything that's transparent, you should not try to do photogrammetry on because it won't work. Equally, highly reflective surfaces like this glass window don't work very well either because the computer through the camera is seeing this building that's reflected in the window as part of the structure, and therefore trying to reconstruct the points from this, but they're not actually on the flat surface of the glass. Obviously, they're reflected from behind you, and that causes problems with it for the camera. If you do have to shoot very shiny objects, for instance, marble's very slightly transparent and is also very shiny, then your best bet is to do so under overcast or cloudy skies, because you end up with diffuse light from through clouds, and that helps cut down on the reflections. You want to try and avoid unwanted objects in your foreground, whether that's people in your foreground or cars. Those can just get in the way. If you can't avoid them, make sure you take plenty of photos from around them so you can cut them out of your model at the end. Again, especially avoid moving objects within the scene. I talked about hair and clothing earlier that move, because the computer doesn't know that objects can move, and doesn't have a way of understanding that movement. It's trying to match objects it sees as being the same, and therefore if something has moved, it's in a different position, but also its relationship to other things around it has changed, and that causes errors. Very flat objects or scenes can often be problematic. The same thing can be we get the same problem with regularly repeating patterns like tiles on a roof or brickwork. However, if you get close enough and get in close for your photographs, there's usually sufficient variation that you can do something about it, and it will recognize that. But from a distance, they look the same, and the computer will have real difficulty reconstructing them. And then finally, vegetation. Vegetation, so grass and leaves, etc., are very difficult to record because it moves in the wind, it's thin, and often is slightly transparent to light, and therefore doesn't reconstruct well. However, if you're just recording a building, then usually the level of noise and the error in the reconstruction isn't a problem, because you just end up with a sort of general green fuzz of background of vegetation, and that can be okay in your scene if you need it to be. You just won't get all a very high detail, but probably you don't want very high detail in grass and trees, etc. anyway. What equipment do you need? Well, it used to be said that you needed a high resolution camera. That's no longer true, because most people's cameras are 5 megapixel or beyond, including your mobile phone's camera. Most mobile phones nowadays have at least 10 megapixel cameras, if not higher. Most digital cameras are at least that much as well, and you can even use drones if you want to, and if it's legal to do so where you are. Be aware that drone cameras often have a fisheye lens, and that requires you to correct that a little bit sometimes. So you want to avoid ultra wide fisheyes and fisheye lenses. Your best bet is something with a fixed focal length, like a 50mm lens. It doesn't have to be. You want to try and avoid zoom lenses, the ones where you can change the focal length. That causes more problems for the reconstruction. It's not impossible, but it is well more problematic. And then in terms of general setup, the same rules for good photography apply to photogrammetry. You want good photographs to get the best result from your 3D modeling. So you want low ISO if you can set it. Obviously with a phone you may not be able to. So anywhere between 100 and 400 generally gives you low noise. You don't get lots of grain, which causes problems. So that usually is a good enough setting. And if you've got plenty of light, that's not a problem. In terms of aperture, if you're using a camera, mobile phone, then you want to set your aperture between f8 and f16. So a small aperture to give you lots of depth of field. However, if you're using a mobile phone, you probably can't set your aperture, because most mobile phones have a fixed aperture lens. White balance. So white balance is how the camera compensates for slightly different variation in the color of the light around you. Usually because you're indoors and using light bulbs of some sort, whether those are strip lights or normal bulbs, then those often have a color temperature, we call it, or a color to them, and they may not appear perfectly white. You want to, so your camera can usually compensate for that, and it does it automatically if you've got it set to auto. But that's a big problem for photogrammetry, because when you create your color texture at the end, you'll get patches with different colors appearance from the same area, and you'll end up with a very odd appearance to the colors of your object. So you want to take it off auto and set it to something fixed. In good bright sunlight, you probably want to set it to about 6,500 K, that's Kelvin temperature, if it gives you that option, or it might just have a sunlight or cloud setting. Pick one of those, and have it the same throughout all of your photography, and that should work fine. If you can, if your camera will support it, then recording either RAW or TIFFs and then converting them to TIFFs helps, but most cameras that may not be possible, and you can use JPEGs, which is what most phone cameras, for instance, will create, and they'll work just reasonably well. They'll have very minor errors that TIFFs are better for, but you'll still be fine for most modern cameras. Take the images at the maximum possible resolution you can. You want to get the most information on the sensor from your subject, and keep the images as they are when you shoot them. So don't crop them, or don't change them, like resize or rotate or any of them. Keep them exactly as they are. So a bit more on camera setup. Take more photos than you think you need. If you're following along a facade, for instance, or following the front of a building, you don't want to be standing in one position and pointing the camera at different angles. Remember, you need multiple photos of the same point. So working your way along the facade, along the front of a building or a facade, is good. You can do multiple positions from each of these points along the facade. That works. Just don't have a single point where you rotate around. Inside buildings, then the same thing applies. You don't want to be stood either in one position or a couple taking photos like this. Rather, you want to be stood as far from the wall that you're photographing and photograph it. So stand on the opposite side of the room and photograph across the room to get the most information in, and then work your way around with your back to the wall, photographing the opposite side, and that will give you the most information. You might have to do a bit of this if you've got a pillar or a column or something in the room to get around it, but generally this works. Because remember, you need to see your geometry from at least two cameras. You need to get lots of overlap between your cameras. The more overlap, the better, because the more that the camera can recognize common bits of parts of the scene, and therefore recreate it better. You want to fill the frame with your subject. Get as much in, so that you don't waste any of your frame, and therefore waste any of the image. You don't have to have the whole building or the whole object in the photograph. You can get in close and take photographs of parts of the building or the object, particularly where you've got lots of detail that you want to cover. Just make sure that you cover enough overlap with your wider shots of the whole building to make sure that you can place those detail shots within the general scene. You need good lighting, and you should avoid flash, because the flash causes very harsh shadow, and shadows the computer will see as features, but if you use a flash and you move around, the position of those harsh shadows moves with the flash, and therefore the features aren't won't be able to be reconstructed very easily by the computer because they move relative to the rest of the shape of the building or object. And finally, you need a couple of markers, at least two, but I tend to take more, where you know the distance between them on the object. So you need to take a tape measure with you and measure something on the object that you can recognize, something distinctive, and make a note of it. You need that in order to scale the 3D object once it's been reconstructed, because the computer doesn't know how big the object is. It does everything relative to each other. So you need to give it some fixed sizes and it'll scale everything to that. So here's an example. Sadly, all my archaeological sites that I've taken photogrammetry of are on my computer at work, and because of COVID I'm at home. So I went to my local church during my daily exercise and took lots of photos using my mobile phone to show that it was possible. These are all taken from ground level, and I'll talk about why that's a problem in a minute. But this is 375 photos around this church, which is up the road from me. My mobile camera is 12 megapixels, so a pretty normal mobile phone camera. I didn't use any masking, and there's some noise. You can see white noise on the edge here. We'll talk about that towards the end of the session. This is a very rough photogrammetry reconstruction. This is the point cloud. This isn't the textured final model. And you can see there are some objects in my scene, these grave monuments, that I had to work around in order to be able to reconstruct this wall. Here are my camera positions. So each of these blue rectangles is a camera position or a photograph. And you can see I started out quite wide, working my way around the building. But around this side, there's a wall and a road, so I couldn't get further away from the building. And these white gaps are holes in the data where the computer hadn't got enough information to reconstruct the surface of the roof. And that's because I couldn't get far enough back. Whereas this side, where I could get further back, we've got lots of good data. But you can see I'm working my way around the building, and then I go in closer to get lots of detail. So these are the holes in the roof. They aren't really there. They're just holes in my data. And that, again, because this side was where that road is, I couldn't get far enough away. And the blue arrow is, as I mentioned before, is what we call sky noise. And that's because I didn't mask up the images when I was doing the reconstruction in the photogrammetry software, because I wanted to do this very quickly. If I was doing this properly, I would go back and make sure they're all masked. So some final points on how to collect the photography. You want to avoid very bright sunlight because of the shadows. Cloudy days are perfect. You end up with nice soft lighting, that's great. You want to avoid rain because the computer will try to reconstruct the position of the raindrops if it can see them in the photos, and that's obviously a problem. And if you've got vegetation or trees and things, you generally want to avoid windy days. You also want to avoid that for very tall buildings. So my previous place I worked had a building, a very tall tower block, where up on the top floor, the building moved about a ½ meter to a meter in high wind back and forth in terms of how much it swayed. Now, obviously, if I was reconstructing that with photogrammetry, then that would cause some errors. You need to work systematically. As you saw in the church photo, I worked my way around and follow the pattern. Take lots of notes and draw lots of sketches whilst you're on your scene or wherever you're recording. The more notes and things you've got, the better. You will use them later on, and they're becoming really helpful when you're trying to do the reconstruction. Make sure you remember to record some ground points and the distances between them. They're the red dots on my sketch here. So the sketch doesn't have to be anything special. It can be very basic, as you can see mine is. But I've marked on mine the shape of the church. I've got the buttresses at the side because they're useful points to recognize in the images. And I've also made a note of where all the windows are and the doors are. just because they're useful things to be able to refer back to. And my ground points are on each of the buttresses, on the corners, easy to identify, and they're the red dots. And in my notebook, I've got the distance, the tape measure distances between these points, so that I can reconstruct them in the, well, I can use them, sorry, as ground anchor points and scale my 3D model to these. I was lucky because this building is a nice 90-degree angle here, and so I can get a nice L-shaped set of points, and that's ideal because I can say this distance is 0. I can say this point is 0, 0, X and Y. I can say these are all X direction, but they're 0, Y, and all these are all 0, X and distances in Y direction. And that makes it nice and easy to define the points. If I was doing this church again, and I will go back and re-record it, then to get higher up, because I couldn't get close and far enough from the building because of the wall and the road, then I would have put my camera on a tripod or on a selfie stick. So this is a very cheap, I think it was about $5, little camera phone mount. So this is my phone in it, and mine came with a little remote control. It's Bluetooth, so I could stick this on the end of a selfie stick or a long pole, hold it up in the air and press the button and get it to take a photo. Very good way of doing things. The only thing you have to remember is to take many more photos than you intended, because you can't see where your camera is pointing. I've done this before on sites where I needed to get high up and we couldn't use a drone, and we used a paint decorating pole, the sort of pole that you have a paintbrush or a paint roller on the end. We took the roller off, we taped the phone mount to the end of it and held it a long way up in the air, and I think we got about 2.5 meters to 3 meters up, which is pretty good, and it allows you to get more angles on the building, and that would have allowed me to get the roof structure. Once you've got your photography, then you need to go and process it. And this software that you use is very computer heavy. It uses a lot of resources. So you need a reasonably good computer. You can use slightly older computers, they do still work, but they'll take a lot more time. And there is a limit to how big a model you'll be able to do. So you'll have to break it all down into smaller pieces. So you need a powerful computer processor and a good graphics card. Lots of RAM. It says here 16 gigabytes of RAM, although my laptop does manage to do smaller objects with only 8 gigs of RAM, but 16 is certainly better. A good 7th generation processor if you can. And I'm going to show you 2 different types of software in a minute. That's where we go next. One of them does everything for you. You put the photos in, you press go, and it works its way through all those steps of the process automatically. That's called Meshroom, but to use that, you have to have an NVIDIA graphics card. So look for the NVIDIA logo on your laptop or computer, or if you're building a computer for this, for a laboratory, for instance, or for doing commercial work, then make sure you pick NVIDIA graphics, because AMD's graphics doesn't work with Meshroom, which is very frustrating. There are a range of different softwares. Some of them are free, some of them are expensive, paid for, and some of them are very expensive. So, for instance, this one, Pix 4D Mapper, is $350 a month. Whereas Photosynth, Open Drone Map, and Meshroom, which is not on this list, it was further down, this is taken from Wikipedia, are all free. If you're a Mac user, then you're a little bit more restricted. So Metashape, which is the other piece of software I'm going to show, which isn't free, but there is a student license, and there's a short trial version, which we'll talk about in a minute, for 30 days. It works on Macs, but a lot of the other software doesn't. So the 2 bits of software. Alice Vision's Mesh Room, which is the one, the first one I mentioned. It's free, it's open source, so you can, if you're particularly competent with computing code, you can alter it. It's excellent quality. It also is a single button, press go, and it does everything. Metashape, on the other hand, is paid for. There's 30 days for free. You can download it. You get to use the full version. It works completely. So I would suggest you download it and have a go for 30 days. And if you're a student or a lecturer, then it's only $60 for a license, which is a lot cheaper than the full version. The pro version, which isn't included in the student license, can also do more advanced stuff like digital elevation models and export to GIS, but you probably don't need to worry about that. There are ways around that anyway. It's excellent quality and it's fairly user-friendly, just as Meshroom is as well, which is why I've picked these two pieces of software. So the first one, Meshroom. As I say, it only works with NVIDIA graphics cards, which is frustrating. But if you've got an NVIDIA, and most laptops and things do use NVIDIA, then it works very well. I'm grateful to Dr. Nabil Maharib from Beirut Arab University, who I co-taught this presentation for the Lebanon core part of the course for these image slides, because I don't have Meshroom because my graphics card is not an NVIDIA graphics card, and so I can't use it, which is very frustrating. And so I'm using his images, so I'm grateful to him for those. But this is Meshroom. It's very simple. You start by dragging in or opening your images, your photos here. You can view each of whichever photo you have selected here in the image viewer. You press this button, the start button up here is usually green before at the beginning. You press that, and you can see that you have a progress bar up here. Once it's done some 3D reconstruction, you'll see the 3D shape here, and the settings for that 3D viewer are over the side. The process is, so yeah, you press the button. The process down here, these are called nodes. This is what it's doing. So these are the feature extraction, image mapping, depth mapping, etc., and through to texturing. These are the steps it's doing in the process, but it just flows from one to the other, so you don't have to do anything. But it also shows you which step it's working on and how far through it is on that, with the progress bar also in each of these steps. And if you click on one of those steps, it will give you the settings and a log of what's going on over here. But basically, you put the images in and you press start, and it either works or it doesn't. Sometimes it doesn't. So Meshroom is very simple. Some example get out. Well, in the middle is a picture of a plant pot. And as you can see, it did not reconstruct very well because these leaves are moving, they're shiny, and they're a little bit see-through. And so the computer can't reconstruct them. And that's corrupted the other parts of the 3D scene. This little statue of Santa Claus that from Nabil, he uses as a test piece, reconstructed fairly easily. This took 50 minutes, not very many photos, it's fairly quick, and you get a reasonable model. If you don't have enough cameras, in other words, enough photos of the object, it can affect the quality. So on the left here, you can see the pictures of the models of the Eiffel Tower and the Leaning Tower of Pisa. And the reconstruction over here on the right-hand side, the Eiffel Tower is not done too bad, but the detail is not very high. And the Leaning Tower of Pisa, it's really struggling with all these small holes in it. And again, this needs more photos. It has created models, so it's not done too bad, but you basically need to do more photography to get more detail and closer in. As you can see, a lot of this photo is not the subject you're trying to reconstruct, so you could have got much closer. So that's Meshroom. It's very simple. Metashape, on the other hand, is by Agisoft, and this process, it looks very similar. So you've still got a window here where you've got your cameras, but also various stages of the process that you work through. A main toolbar across the top. You've got, just like Meshroom, you've got a 3D image viewer to see your 3D image scene. And you've got a load of pictures down the bottom, where your pictures are down the bottom, so where you can view each of the pictures. This is imagery taken on a drone. This is 52 images, which is a little bit small, but it gives you a general view. You don't get very much detail. And this is in Pristina in Kosovo, so one of the other centres. And I've put this together, probably only took a couple of hours for it to process. And this is the textured model at the end. These were captured on a drone, so with 3 batteries, you can get about probably nearly an hour's worth of flight time to capture images. I think the person who took these photos didn't use all 3 batteries, but yeah, so drone photos, 52 photos. I probably, for this one, if I wanted more detail, probably would have done around 150 to 200 images at least. But 52 does get you a basic model. And Metashape used to be called Photoscan. It's the same software, they just changed the name. Can use either photos, but it can also use video. Video is really just a series of lots of photographs in rapid succession. And so if you give it video, what it does is it picks every so many frames or so many images in the video and saves those as a photograph, and then just uses the same process as it does for photographs. So to add your photographs, you go to Workflow, click Add Photos, choose your location and import them, and it imports them into the software. Videos is a little bit more involved. You go to File, Import, and then down to Import Videos. It will you choose which video you want to import, and then there's a dialog box that asks you. Then it asks you what file name you want to give your photos that you're extracting from your video. How many the frame steps, so that's how many of the frames they want to save as the photo. If you leave it as 1, then if your video is 30 frames per second, it will do every second it will do 30 images. That's probably not a good idea. You'll end up with thousands of photos and it will take forever to process. I usually, because I shoot at 30 frames per second, usually I set this at 15, so 2 per second, in other words. You can set the start and end points where you want. If you've got an introduction or titles on a video, for instance, you can skip past them and then set the start point and the end point. And when you press OK, it slowly imports those into your into the software. Once you've imported your photos or videos, if you want to use that, although I would suggest that photos are always better, you need to test the quality of them. And you do that by right-clicking on one of your photos and selecting this. Here it says Estimate Image Quality. And this will give you an indication of how good the images are. And you can look through the data that it gives you. It gives you a list of the image qualities, and delete any images or remove any images that are not good enough in terms of quality. And generally we think of that as less than 0.65 as a quality indicator. You can also check videos for quality as well, but to be honest, it works exactly the same, because once you've imported the videos, they're essentially treated as photographs because they're in individual frames from the video. And so it works the same way. So when you right click on and choose estimate image quality, you can change this icon here and choose list, which will list all the photos with some information about them, their size, etc. And this will give you the column of the image quality. And all of these are good quality images. They're around 1 at this for these images. Sometimes they're higher than that, but there's certainly nothing low enough to end up needing deleting out of this. So Metashape's workflow is very simple to follow, but before we do, there are a couple of tools that can be very useful to help make sure that the software is looking at getting the best data possible. And the first of these is to mask photos. So if by double clicking on any of the photos, it will open it up in the main viewer, as it's done here, in a new tab. And you can see from this photo from my church model that there's quite a bit of sky in it. I've broken my own rule about getting as much in as possible because I was pointing up towards the roof to get as much of the roof in. And the sky and the bright color of either the blue or the white of the cloud will introduce what we call sky noise along the edges of a model. So you can remove that by masking off the sky and telling the computer software not to use this area of the image to create 3D points. And this can be very valuable. The things you want to mask off are obviously sky, but also anything that moves a lot, like trees, if you don't want them in your image, and especially water, because water is both clear, it moves, and it's highly reflective and causes a lot of noise in your reconstruction. So you certainly want to mask off areas, very large areas of water. And you do it using these tools up here. And this one's the loop tool, but the little arrow at the side will give you an option to use a square selection box tool or a variety of other tools. You basically draw around the area you don't want, right click and choose select add to mask, and it will add that area that you've just drawn around to the masked off area of the photo. You don't have to do it all at once, so you could do an area here and then keep building up as you get closer in. So you can do all the large areas very quickly with the square mask tool, and then you can go in and do the detailed shape with this loop tool. Once you've aligned your photos, once you've masked your photos and you've got them and you're ready to start, then the workflow looks like this. If you click workflow, this drop down box opens up. You've got add photos, which you've already done. So then the next sequences are to align the photos, then to build the dense cloud, then to build a mesh, and then to build the texture. But basically you work your way through each of these steps in the workflow one at a time. So you start with camera alignment, and that creates the initial structure from motion and creates a sparse cloud. Once you've done that, you then use the sparse cloud of points to build a dense cloud with much more information and depth mapping in it. Then you build a mesh from that dense cloud, and finally you color that mesh using the photos. So here's the process. We've added our photos already, so we choose align photos, and that results in the sparse cloud. So here's the sparse cloud for the church. You'll notice there's a lot of extra points floating around in the noise. Partly that's because when I first did this, I didn't mask the sky off. Masking off the photos will help with that. And there are some videos links at the end of this PowerPoint presentation with some examples of some videos that will show you how to do masking as well. Once you've got the sparse cloud, however, and if you've got all of these points, you might want to delete some of them so that when it builds the next step, that builds the dense cloud, it's not using these incorrect or points that have got a lot of error in them and noise to build the dense cloud. So you can delete them at this stage, some of them. And you do that by using these selection tools, square or circle, or draw around tools. And you draw around the points with them, and the ones that are selected end up pink. You press delete and it deletes them out the scene, and it removes those unnecessary points and makes the sparse cloud a lot thinner. But it also means that the reconstruction later isn't based on this bad data. That helps reduce the time, processing time of later steps. So to do this, as I say, you hide the photos if you've got them open where the positions, because you don't want to delete your cameras, which you can also do accidentally in this stage. So hide them by pressing that button until they go away, and then use these select tools to draw around the points and delete them. Another check you can do at this stage is to have a look at where your cameras are aligned. So if you click on this box here, it turns these cameras on. You've seen this image already where I showed you where my camera positions were. And this is looking in plan view, looking straight down. However, when looking in through the sides, when I first did this, some of my cameras were below the level of the ground. I know that's impossible. And so you can redo the alignment on just one or two cameras by selecting them in this bottom box, right-clicking, choosing reset camera alignment from the menu, and then right-clicking again on that same image and choosing align camera. And it should, because it's got a lot more points to compare to now as a base model, give you a better reconstruction and put it in the right place. So the next step in the process is to build the dense cloud. If you go to workflow and build dense cloud, now you've got several options when you do that. So when you click on build dense cloud, a box a small window box comes up where you can choose the quality, and you can also choose the depth filtering. In general, never start with ultra high. That will take a very long time to process and may not give you the results so you want. I always start with either medium or sometimes high if I haven't got that many photos, or I'm very confident of how good quality the photos were, and I've collected, for instance, from collecting a scene that I've previously done before. And you can use, if you use high, you can always come back and recalculate the dense cloud at ultra high, or equally if you use medium, you can work your way up. The filtering, it's generally suggested that you use aggressive. Nearly everybody sticks on aggressive depth filtering, and unless you've got that creates real problems and it doesn't work properly, only then come back and work on some of the others. The only caveat to that is that aggressive filtering will take out some points, and so if you've got very fine detail, where you've gone in very close, maybe moderate might be a better option. And once you press OK and set it to build, then you have to wait for a while because it works its way through. And the faster your computer and the smaller the number of photos, the quicker this will happen. In this case, with the church with 375 photos, I think this took about 2.5 hours to do. You can press minimize and let it leave it to do its to finish. You can also, it's using most of your computing resources in terms of the processor and the graphics card and the RAM. So if you suddenly need to use your computer, you need to send an email or something, you can press pause and then you'll be able to resume the process halfway through. But just remember to press resume. So as I say, it takes a long time. So on very low quality, on mild or low quality, it may not take very long. So in this case, for instance, the low quality took 1 minute and 16 seconds for a model with only 93 cameras, whereas when it was put on ultra high quality, it took 36 minutes. Now these are Nabil's photos, not mine. He has a much more powerful computer than me, whereas mine would have taken a lot longer than 36 minutes to process this data. So once it's built the dense cloud, I'm going to take you into this model. The dense cloud looks like this. So this is not a model, but is actually lots and lots of points, and it's so many points that unless you zoom in really close and see where all the points are, it looks like a flat surface, but this is the dense cloud. Again, this is Pristina in Kosovo, the schoolhouse. So this is from just 52 images from a drone. And the quality's okay. Some of this rubble on these balconies and things are not very clear, but it's okay. Just to show you the sparse cloud whilst I'm at it. So that was the sparse cloud. And the reason the roof isn't showing up very much is because of the repeating pattern of tiles, which is causing a problem. And the alignment isn't great on the roof. Now, fortunately, in this case, we're not particularly interested in the roof beyond it showing where it is, so that we can get away with that. I go back to my presentation. So once you've built the dense cloud, the next step is to build the mesh. So you go to Workflow, Build Mesh. And again, you get an options box that lets you choose what some more details. So you can choose what the source data for your mesh is. Now, nearly always that should be the dense cloud. However, if you want to run a very, very fast and not particularly good model, but you just need something very quick, then you can use the sparse cloud data if it's any good. But generally, you want to use the dense cloud. The surface type, I nearly always have it set on arbitrary. And I use that for, you can use that for nearly everything. The only thing that, the only time I don't use that is for what we call planar surfaces. In other words, if you've got a flat wall with lots of where you've had to get in very close to get lots of detail on the brick, for instance, in order for it to be able to tell the difference between one brick and another. If you move parallel to that and move along that wall, then we call that a planar surfaces, and you can use a height field for that, and that works quite well. Equally, if you're using a drone at a fixed altitude, pointing with a camera pointing straight down, and you're just doing general terrain shape to create a landscape, then height field will work as well. And the final option is the interpolation. So if you leave interpolation off, it will only reconstruct areas where you've got dense cloud points. If you enable it, which is where it should be, then it will do some manual hole filling between those points based upon the imagery of the photos. And so nearly always I have it left on enabled. Extrapolate will take it a step further, and it will start to guess between larger holes. I tend to leave that off, mainly because a lot of the photogrammetry I do is used for analysis, and so I don't want it to be guessing and therefore adding in random data to my analysis. So I tend to leave it on enabled, and I suggest you do too. Once you've built the other option in this box is the face count. So in other words, how many triangles do you want it to reconstruct? The more triangles you've got, the greater the level of detail, but also the more likely that noise and error points will end up as in the mesh. And if you use very low levels of faces or triangles, then you only get very basic detail, but you do get a very easy model to open in things like web browsers, etc. So usually I would suggest that you start with a medium to high level. I usually pick medium, and then you can reduce the number of triangles with another tool later called decimate, if it's too high. And you can, by doing that, you can gradually reduce the number of triangles until you get to just the right level, where you don't lose too much detail, but you reduce the overall size of the file, the object file. So this is the decimation tool. So if you've gone for a high level of detail of the faces, then you can use the decimation tool, which is under Tools, Mesh, Decimate Mesh, to reduce the number of triangles down. If you're wanting to put your model, if it's a building, for instance, onto Google Earth, or you want it to go on the web, then the internet, then you probably don't want too many faces, because for every point around the triangle, of the 3 points in each triangle, you've got 3D information to locate it, plus information about which way the triangle is facing, plus information about the color of the triangle, etc. And so that's a very large amount of information when you've got 1.2 million faces or triangles. When you've only got 200,000, it's a lot smaller. So your exported files are a lot smaller and therefore are easier to handle over the internet, etc. Another tool that's very useful after you've created your mesh is the Close Holes tool, which again is under Tools, Mesh, Close Holes. And it allows you to repair some of the small holes in the mesh. And the slider along the bottom lets you set the size of the holes you want to fill. So these little tiny ones are great to fill, and you want to fill those up automatically, and it'll pick the color from the photos. Some of the larger ones are probably okay, but this large one up here you probably don't want to fill, because you'll end up with very large flat surfaces that don't really match the shape of the original object. And then finally, the last step in the process is to build the texture. That's to convert the color information from the photos and relate it to each of these triangles. And to do that, you go to Workflow, Build Texture. And when you do that, you get a box again with some options. The mapping mode, you get a choice. Generally, I'd use it for most objects and buildings. I'd use it on generic. If you're doing a flat surface like a landscape or a planar surface, you can use orthophoto or one of the other methods. But I find generally that generic works fine. The method you should pick is, the default is the mosaic method. And then you want to set the texture size in terms of pixels. So all texture files are square, and they're usually a power of 2 in terms of how many pixels wide and how many pixels tall. So that's usually 1024, 2048, or 4096. And I tend to use either 2048 for small objects, and for buildings I tend to use 4096. But it usually defaults to 4096, so I'd leave it on that unless you've got a small object. And then you need to export the model. So to do that, you go to File, Export, Export Model. You give it a name, and you choose what sort of file you want to save it as. And I would always suggest going for OBJ or Wavefront OBJ. This is a format that's recognized by many computer software processing suites, mainly because the company that owned Wavefront OBJ is no longer in business. Nobody owns the copyright on this file format, and so everybody uses it, and it's nice. It's very simple to code. It's almost human readable, because it lists the 3D coordinates of each point, then it lists their position on the texture format file, etc. So it's systematic and fairly easy to read by any computer. You click save, and when you do that, it will give you an options box. Generally leave everything as it is. You probably want to export your texture as a JPEG. Okay, and press OK. The exported model, when it exports wherever you told it to, saves as 3 different files. So I called mine Schoolhouse, so they all end up with the same name. The first file is the OBJ, that's where all the 3D information is, and you can see that's the largest. In this case, for the Schoolhouse, it's 289 megabytes. Then there's the texture file, which is a JPEG, and you see that's 2 megabytes. And then finally, a .mtl file or material file, and that links these other 2 files together. If you're building 3D objects from scratch, instead of using photogrammetry, sometimes that will include color information that you've applied as a material, but that doesn't work in photogrammetry. So that file basically just links these other 2, and therefore is very small. There's only 1 kilobyte. And you need all 3 files when you upload them. So once you've got your object, 3D object, you might want to upload it to Sketchfab. And Sketchfab is an online repository for sharing 3D models. There is a free account, which limits the number of models you can upload per month. However, you can also get a free pro account if you can convince them that you're a museum. And what they think of as a museum is really a cultural heritage specialist group carrying out work and not making a profit from it. So we've convinced them at Leeds, myself and Jehan have managed to convince them that the projects that we work on with public engagement and youth engagement using cultural heritage is exactly the same thing as a museum, and they're fine with that, and they've given us a free pro account. You just need to email them and ask. And if you make a good case, they're usually very good. To upload your model, you click, once you've logged in, and you click on this upload button. That brings up a screen, and you select the files for your model. So you need the OBJ, the JPEG, and the material file. You select those, and then once you've done that, then it begins to upload. Whilst it's uploading, or when it has uploaded, you'll see the progress here on the left-hand side. Then you can add some information. And this is what's going to be seen next to your model on the web front end of Sketchfab. So you give it a title, you give it a description, and in that description you can type in Arabic as well. It doesn't write a line, which is very frustrating, and there's something I've asked them to include, but it doesn't yet, I don't think. You can also decide who sees in this panel over here, who sees the model. So you can leave it so anybody can see with a link can see it. You can say everybody can see it, even whether they've got the link or not. So you can generally just see it on Sketchfab, or you can make it private. You can also put age restrictions on if your 3D object isn't appropriate for children to see, although usually in cultural heritage that's not a problem. You can also choose what happens if people want to download your model, what they downloaded it in, and I would usually leave it as original format. And then you press save, and once it's saved, once it's uploaded, and when you've saved all this information, then you press publish. This button will be slightly different depending what you choose up here. Once you've done that, and if it's successful, you get this green tick, and you then get a link to see your model. So click on that link, or copy the link to your model if you want to upload or embed it in a web page. And that's it. That's photogrammetry and how to upload to Sketchfab. The best way to have a go at this is to download Meshroom for free if you have an NVIDIA graphics card, and or download Metashape for 30 days for free. Take some photos with your mobile phone of an object. Start something, either an easy building that you can work around, like my church, or you can use a small object like an ornament, etc., or something like that from in your house. Take some photos around with a camera or your phone, put it into the software and see how you do, and learn and practice with it. Start with a few photos, probably about 30 or 40 photos, and see what sort of model you get. If it's a bit lacking in detail, add some more in. With Metashape particularly, you can always go back, add more photos and reprocess. Can't do that with Meshroom because you just end up having to redo the whole lot. That's fine. And just try it out. I've included here some useful videos on YouTube, some tutorials. The Metashape ones may refer to the software as Photoscan. As I say, it's the same software. They've just recently changed the name. These two videos are part 1 and part 2 of a tutorial series. Part 3 isn't really relevant to cultural heritage, but part 4 is about buildings. So have a look at this YouTube contributor and look at his other videos. They're very good, really good, a good way to take you through and show you the process. These masking photos are useful information. Some of them are a little old and use much older versions of Photoscan, but the same principles apply. And the Meshroom photos tutorial is pretty good. And that's creating 3D objects for cultural heritage from photos using photogrammetry. Okay.